Welcome back to Operating Systems Crashcast. I'm Victor, and with me, as always, is the brilliant Sheila. Today, we're wrapping up Chapter 3 on processes with a comprehensive summary. Sheila, are you ready to dive in?
Absolutely, Victor. I'm excited to recap this crucial chapter. Processes are the backbone of modern operating systems, and understanding them is essential for anyone in the field of computer science or software engineering.
You're spot on, Sheila. Let's start with the fundamental concept of a process. Can you give our listeners a quick refresher?
Of course, a process is essentially a program in execution. It's the active entity that represents the running state of a program, including the program counter, stack, and data section. Think of it like a chef following a recipe in a kitchen. The recipe is the program, and the chef actively cooking is the process.
Great analogy. And just like in a busy kitchen, we often have multiple processes running simultaneously in our computers. This brings us to the concept of process scheduling. Can you elaborate on that?
Certainly. Process scheduling is how the operating system manages multiple processes competing for CPU time. It's like a traffic controller directing cars at a busy intersection. The scheduler decides which process gets to run next based on various algorithms we've discussed, such as first come, first served, shortest job first, or priority scheduling.
Excellent explanation. Now let's talk about the life cycle of a process. What are the main operations that can be performed on processes?
The main operations on processes include creation, termination, and state transitions. Processes can be created by other processes, like parent-child relationships, or during system startup. They can transition between states like ready, running, and waiting. Finally, processes can be terminated either voluntarily when they complete their task or forcibly by the operating system.
That's a great overview. Now, one of the most intriguing aspects of processes is how they communicate with each other. Can you explain inter-process communication, IPC, and why it's important?
Absolutely. Inter-process communication is crucial for cooperation between processes. It's like how different departments in a company need to share information to work effectively. There are two main models of IPC: shared memory and message passing.
Could you give us an example of each?
Sure. Shared memory is like a whiteboard in an office that multiple teams can read and write on. Processes can exchange data by reading and writing to a shared memory region. Message passing, on the other hand, is more like sending emails. Processes exchange messages through the operating system, which acts as an intermediary.
Those are great real-world analogies, Sheila. We also covered some specific IPC systems in this chapter. Can you highlight a few?
Certainly. We discussed POSIX shared memory, which allows processes to share parts of their virtual address space. We also looked at pipes, which are particularly useful for communication between related processes. Another interesting example is message queues, which provide an asynchronous communication protocol.
Excellent summary. Now, let's zoom out a bit and talk about how processes communicate in client-server systems, which are ubiquitous in modern computing.
Right, client-server communication is a fundamental concept in distributed systems. We covered three main methods: sockets, remote procedure calls, RPCs, and pipes. Sockets are like phone lines between processes, allowing them to send and receive data. RPCs make network communication look like local function calls, hiding the complexity of network protocols. Pipes, as we mentioned earlier, are useful for local inter-process communication.
That's a great overview, Sheila. As we wrap up this chapter, what would you say are the key takeaways for our listeners, especially those preparing for interviews?
Great question, Victor. I'd say the most critical points to remember are: 1. Understanding the process concept and its components. 2. Knowing the basics of process scheduling and common algorithms. 3. Being familiar with process operations and state transitions. 4. Understanding the importance and methods of inter-process communication. 5. Recognizing the differences between shared memory and message passing. 6. Having a basic grasp of client-server communication methods. These concepts form the foundation of how modern operating systems manage and coordinate tasks. so they're crucial for anyone working in software development or system administration.
Excellent summary, Sheila. I'd also add that it's important to understand how these concepts apply in real-world scenarios. For example, how multi-process architectures are used in web servers to handle multiple client requests simultaneously, or how IPC is crucial in microservices architectures.
Absolutely, Victor. The practical applications of these concepts are everywhere in modern computing. Understanding processes helps developers write more efficient, scalable software and helps system administrators manage resources more effectively.
Well said, Sheila. As we conclude this episode and Chapter 3, I want to remind our listeners that processes are just the beginning. In the next chapter, we'll dive into threads, which add another layer of complexity and efficiency to process management.
I'm looking forward to it, Victor. Threads are like lightweight processes, and understanding them is crucial for modern concurrent programming.
Absolutely. Well, that wraps up our summary of Chapter 3 on processes. Thanks for tuning into Operating Systems Crashcast. Until next time, keep those processes running smoothly.